Okay, so the next section of the course is on alkanes, and what we're going to see is that the alkane functional group, as everyone knows, contains only carbon-carbon and carbon-hydrogen single bonds. And alkanes are basically going to make up the backbone of all of our you want to review how we got the products and acids at the end of the test? All right, we could do that. Let's see here. Let's see. Okay, so I'm going to share something new. Whiteboard. Now, I can't remember exactly what any of the questions were, but we can do this. Okay. Okay, so let's pretend that we had something like this as one of the molecules and something like this. So and we had one basically we stipulated that there was a one-to-one mixture of each one of these molecules. So, and then there was products here, products. Oops. And then there would have been a whole bunch of potential answers that we'd drawn. And the hard part was coming up with wrong answers, in all honesty. So what would a possible answer be? Oh, no. Let's think. So if this is an acid-base reaction, I'm just trying to think of a good bad answer here. That's a problem with multiple choice tests, is coming up with wrong answers that look reasonable. And what I should have done over the course of my career is kept everyone's wrong answer from all time so I could use those, but I didn't have the forethought to do that, so it's a bit problematic. So what we need to basically decide is which compounds the base, which compounds the acid. And then remember, these reactions we're transferring H plus. So the base should be grabbing the proton, and then you'll generate a conjugate acid and a conjugate base. So in this case here, if we came to the conclusion that this molecule here was the base because This molecule over here has an acidic proton right there. We could say, well, these electrons are probably going to come along and grab this proton, and those electrons are going to move there. And that's going to generate this compound here, which would be the conjugate base, and this compound over here, which would be the conjugate acid. Now, there was a previous question on the test in which basically the products and the reactants were drawn, and then the pKa values were given for each species, right? For each acid, for the acid and the conjugate acid. Now, when I basically did a quick survey of everybody's score on that question, the score on that question was really, 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 really good. So conceptually, the idea that you make the weaker acid and the weaker base throughout the course of the reaction, everybody seems to get that. So that's excellent. The trick for these types of questions is, number one, we don't have pKa values. So you need to decide, is the product, like the conjugate base versus the base, like we're going to compare these two. This one, we're going to be comparing the two of them and see which one is more stable. Because remember, we're going to produce, when it comes to a negative charge, the more stable the negative charge, the weaker the base. So we'd be comparing this negative charge here to this negative charge here. And if it is more stabilized, and it is if the conjugate base is a weaker base, weaker than the base, then these should be your products. So in this case here, you got a carboxylate. So this is a carboxylic acid, which has been deprotonated. And over here, this is a phenol proton. So the carboxylate is stabilized by resonance on electronegative atom oxygen. Whereas over here, this negative charge is stabilized by resonance, but it's stabilized on carbons in the ring. So this reaction should go, these should be your two products. Now, I think there was like some other wrong products in there, or no reaction stuff. I just tried to move the proton around in such a fashion that it would, to make the incorrect answers seem at least moderately reasonable, but I can't remember any of them off the top of my head. Was there something more specific than that? Was it Brett or Brent? I can't remember who asked that.
Yeah, it's Brett.
Brett.
No, there wasn't, I think, anything. I mean, yeah, on the test probably there would have been something specific, but yeah, we can't remember what the specific questions were. But no, I think just having some of the wrong answers in there then made me second guess what the correct one was and all that stuff. So yeah.
Yeah, it's too bad that what would be ideal for if I had my ideally it would be nice to be able to use the little ChemDraw program to draw stuff, or a little whiteboard just to draw stuff and have that as it, but they don't have that as part of the test yet. So that's that would be better, because there's yeah, so because that would be like when you just basically let people write what they think. That's a better way of doing it than providing a host of answers and that type of thing. So yeah, it's just one of the unfortunate things with regard to the way that the limitations on that type of testing, which is,
I think there were couple questions that weren't, how do I put it, like this simple. Like it wasn't just moving a hydrogen, or I think some of the questions had a metal or transition metal added in.
Okay, yeah, I think I remember one of them. Okay, so there's some more stuff on the chat here. Do, 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 do. Okay, so yeah, this was okay, so here we go. This was one of the questions. Something similar to this. Plus. And then products. And then there was a host of answer. Oh, there might have been a double bond here or something like that. Yeah, this. And there was a host of answers like this. And there was two options for this one. There's two options. So what are, like, if you've got, okay, remember the carbon lithium bond is technically covalent. So we have to draw it in such a fashion. Now, the neat thing about the carbon lithium bond is that which direction is this polarized in? Which side's got the negative charge, carbon or hydrogen? Right, carbon. So it's polarized in this direction. So this is basically saying if we wanted to just remove that lithium entirely, if we wanted to think about it, this would be carbon with a carbanion and lithium plus off somewhere to the side. But it's really a covalent bond. So in this case, the lithium is on a sp3 hybridized carbon. And remember, one of the various things that acidity was based upon was we had, okay, there was the atom itself, which could involve two things. It could involve electronegativity and atomic size. There was resonance effects. There was induction. And there was, of course, the hybridization part. And so, because sp3, if we were to have a little energy diagram here in the corner, sp3 orbitals would be here. And as you increased the s character, the energy would actually be lower and lower and lower. So if you've got a negative charge in an sp3 hybridized orbital, it's higher in energy and it's going to be more unstable. And as you change the hybridization, it goes down and down and down. So an sp3 hybrid, so acetylene here, the simplest, like the pKa of this is approximately, I think it's 22 to 25 pKa. Whereas with methane, it's up at 50. So there's a massive difference in acidity. So an sp3 hybrid carbon, a negative charge on there is really, it's the most basic thing you can find. So what we're doing is we're just looking for protons on this molecule which are in a different type of hybrid orbital. So rather than drawing it with a carbon with a minus, all I've done here is this is the covalent bond. It's still polarized in this direction, so it is still technically carbon with a minus, but the lithium is still attached because the carbon-lithium bond is covalent. So out of these three, this carbon, let's change the color of my ink. This carbon here is, no, that's wrong color. This carbon is sp. If it was on this one, it would be sp2. And if it was on this one, it's still sp3. sp3. So the product should be something like that. So if I maybe if I'd done the question, it was just carbon with the minus without the lithium there, it might have been, that might have been easier, I suppose. But yeah, carbon lithium is a covalent bond. So, and in fact, you can buy this in a bottle. It's very reactive. It basically reacts to oxygen in the air. So the bottle is sealed with a, and it's packaged under inert gases, like typically it's nitrogen. So it doesn't catch fire and all that sort of fun stuff. Oh, and if you take natural product synthesis, for all of you chem majors, we get to play with that. So that's always fun. Yes. All right. So was there, yeah, so carbon, I guess the key point is the carbon lithium bond is basically, it's covalent. So, but you can think of it as C minus and lithium plus. But one of the things that you, when I've done that before, remember, this lithium on the this covalent bond isn't an empty, its orbital isn't empty. Like in the past, some students have viewed this as a Lewis acid because of the lithium, but it's only a Lewis acid if it's lithium plus, not if it's actually attached to something. So. All right, so clear that up. There was a question about, do I know the average of the scores so far? I guess I could look that up. I didn't pay close enough attention. I was too busy scanning through this because there was lots of questions where there were zeros given. And then I'd go and look and people got like 3 out of the 4 right. So I don't want to give anyone a heart attack by saying what the average was until I've gone in and changed the marks a bit. Yeah. Were there any other, what we can do on, yeah, I'll hope to hand those back next, as soon as I get the extra, when I add the part marks. Did I miss anything else in chat? Yeah, there is a, right now, if you go into the grade book, it's going to tell you what your raw score is. But there's no part marks in that. That's just, if you got anything wrong in the question, the computer just marked you wrong. So that's the problem if you go and look at that right now. But there's an option for the test which basically says hand back, and when you go into into each question, I can add comments to stuff. So I can say, you know, one of the questions that people missed a lot was just, which was interesting. Okay, so let's say this is our molecule. And I said, how many carbon atoms are there?
Wouldn't there be 5?
1, 2, 3, 4. Yep. And how many hydrogen atoms are there?
7?
3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 8. I got 8. Okay. Number of sigma pi bonds.
I count 2.
Sigma. This is the one which was there was issues with the sigma bond one. And I think it's because we haven't drawn all of the hydrogen atoms on this, right? So you would have like 1 sigma bond for a hydrogen here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, so it was one of the, this was one of the surprising things, which that was, so for each pi bond which you see there, there's actually a sigma bond underneath it. So that's, and then the hydrogens are the ones which, since they're not drawn, it's kind of hard to, but anyway. So because people got this one wrong, and they got all 3 of these right, there was a bit of, so that was just one of the things I noticed immediately. So, right, if you've got a double bond, it's made up of a pi bond and a sigma bond. Because the first bond, if you got, say, 2 carbon atoms here, the bond here in the plane is the sigma bond, sigma, and then the orbitals, they make the overlap above and the overlap below, that is the pi bond. And so when we draw these orbitals in such a fashion, it's almost like half this bond is above and half this bond is below to make it the 1 pi bond, you know? So yeah, so a pi bond has got, like when you see a double bond, that's made up of a sigma plus a pi. All right. Let's. All right, so were there any other questions, or should I go back to the, yes. And if you've got a triple bond, that would be 2 pi bonds and 1 sigma bond. Yeah, that's right. So 2 of the orbitals would be in the plane of the blackboard. We could have 2 of the orbitals, which would be flat. This one's going back into the blackboard. So there's overlap here, overlap there, overlap there, overlap there. And then the sigma bond, which I've already drawn, let's draw it in red. Sigma bond would be right there. Sigma bond is made from hybrid orbitals. And the pi bonds, oops. Sigma bond is made with hybrid orbitals. The pi bonds are made with p orbitals. Yeah. Okay, let's clear that. All right, now let's go back to okay, let's go back to, I can put this up so it's not laying flat. All right, so I think in other classes, what I've been told some people do is they assign someone to be the chat monitor. So if there's a question, they can say, oh, can you stop? There's a chat question. So if anybody wants to volunteer to be the chat monitor and just interrupt me and let me know that there's a question, that would be super. I would not oppose to that. Not be opposed to that. Okay, so with regard to, all right, thank you. So with alkanes, okay, so carbon and hydrogen single bonds, and they're going to end up making the backbone of all of the compounds that we look at. So they are, what we're going to see is they're not particularly reactive compounds. So this is why we deal with them first. So some alkanes can be very large or very small, and it really just depends upon the number of carbons. And the general formula for alkanes is if you've got some number here, the H's will be 2 times that number plus 2. So in the case of methane, where there's 1 carbon, the hydrogens would be 4. 2 times 1 plus 2 is 4. And if it's ethane, which is 2 carbons, you would have 6 hydrogens. And so because alkanes, there is no double bonds, and every carbon atom is bonded to the maximum number of hydrogens that they could be, or carbons for that matter, we say that they're saturated in hydrogen. So you can't add any more hydrogen to your compound. But if you've got like an alkene, a double bond where there's a carbon-carbon double bond, you could actually add hydrogens to those carbons. So alkenes are what we call unsaturated compounds. So alkanes are saturated in hydrogen. So let's see here. If you take let me draw something again. Hopefully I can draw this correctly. Now, this compound here isn't an alkane, but it's going to give you sort of a idea of what. So, so you take some oils from different sort of plants or animals, triglycerides, and they've basically got a glycerine as which is a little fragment way over here. And there's some functional groups in here. There's some ester functional groups. And there's basically these straight chains. And there's usually double bonds in them. And they tend to be cis, naturally occurring, tend to be cis. And you've probably all heard of saturated fat and unsaturated fat, right? And that trans fats are bad and this and that. Well, what's going on here and how you get a trans fat is that when people were starting the food industry, they realized that you could make tasty things like peanut butter out of peanut oil by converting these double bonds into alkanes. So by doing a reaction with hydrogen, which would be called hydrogenation. And you'd react these with hydrogen, and the double bonds would become single bonds, and it would convert the oils into solids, and then you add a bit of salt and a couple other ingredients, and boom, you've got tasty peanut butter. And during the process of this hydrogenation reaction, they use a catalyst, and sometimes it doesn't actually completely react with the double bond, but it converts it so it's got a different structure. So the two ends are on opposite sides. So that's, you probably heard of like saturated fat and trans fats and that sort of stuff. Well, that's basically where all this sort of stuff comes from. So hydrogens themselves are, alkanes. Let me go back to the original slide. Alkanes are saturated, so you can't add any more hydrogens to them. Anyway, okay, so let's go to the next slide. Right. Now, alkanes are also called, there's a historic name called aliphatic compounds. So if you ever hear the term aliphatic, usually that was used in conjunction with aromatic. So aliphatic was non-aromatic alkanes. Aliphatic compounds were alkanes, and then aromatic. Those two sort of were little brothers and sisters back in the olden days of organic chemistry. And that name is sort of stuck around. There's a couple of old names that have stuck around. So here's some examples: methane, ethane, and they're pretty simple. Remember, each carbon, because it's bonded to 4 things, each carbon in these sort of structures is going to be tetrahedral. They're all going to be sp3 hybridized. With 3 carbons, the name is propane. But once you get to 4, so anything above 4, then there's different ways to connect the carbon. So you can have a spotlight. You can have just a straight chain sort of structure, and we always draw these straight chain structures as zigzags. And the reason why chemists are really OCD about this, or organic chemists are OCD about this, is because the zigzag structure sort of helps to visualize the fact that it's tetrahedral. So that's basically why we do that. And then or you could, instead of all 4 of these being in a line, you could actually connect one of the carbons to the middle. So what we're going to see is that these ones that are, oops, I didn't mean to draw there. Erase that. Oh yeah, I guess we should talk about this first. So they've got the same molecular formula. So it's C4H10, but they've got a different connectivity. And the name for these types of compounds is constitutional isomers. So, and in the next section of the class, we're going to talk about stereoisomers and stuff like this. So, and those are compounds which have got the same connectivity, but a different spatial rearrangement and stuff. So this has got 4 carbons, straight chain. This one is what we'll call branched, 4 carbons, but they're constitutional isomers with one another. An isomer is apparently Greek for made of the same parts. So that's where that word comes from. Questions so far?
There's been none in the chat.
Okay, perfect. So, right. So if your alkane is basically only connected to a maximum of 2 carbons, and we draw it in this zigzag fashion, we call these straight chained alkanes. And they're given a little prefix. If you ever go to in the lab, if you have to go get some hexanes, which is 6 carbon, and it's got a little, you look at the bottle and there's a little N in front of it, that means that all of the hexanes in that bottle should be straight chained. So this little N prefix is for a straight chained alkane. And if there is no, if it just says hexanes, mixture of isomers, then it's going to be a mixture of the straight chain and the branched. And there'll be a whole bunch of potential branched hexanes out there. And here we've got a branched alkane. 1, 2, 3, 4, 5, 8. So 8 carbons. And we just put this little CH2 here in the middle. And when it comes to the one thing that there's basically 2 types of reactions that are quite common with alkanes. One is radical reactions. They react with free radicals. We'll see that later on in the class. And the other thing which we would use these for in our day-to-day lives is in our fuel tanks of cars. So they're combustible materials. And it turns out that branched alkanes like burn, they've got a higher octane value for them. So they are sort of preferred with regard to in the construction of, in the use of fuels. So, but as time goes on, we'll probably see less and less cars that run on actual petroleum, given the way that the world's going. All right. Okay, so there's the part of the class which we're going to have to sort of use some mental, sort of put into our mental memory, I guess, is the names for some of the smaller molecules. So if there's one carbon, it's called methane. If there's two carbons, it's ethane. With three, it's propane. With four, it's butane. And five, it's pentane. With six, it would be hexanes, heptanes, octanes, nonanes. But really, for what we're interested in, it's really these five, which are the super important ones. And what we're going to see is that smaller fragments of these are common in organic chemistry. So that's why these names are the ones you will really want to keep in mind. Most textbooks have a big section at this part about naming compounds. It is the most deadly, awful, boring thing there is in the world. So I try not to subject everyone to it. I know it was one of the things that I loathed about organic chemistry, is naming stuff. But there's some really, maybe I'll post a video on, if you're really interested on how to name things, maybe I'll do that over the weekend. Give me a little project to do. But the names that we really want to remember are the methane, ethane, propane, butane, and pentane, and what they correspond to. So just keep that in mind. Okay, so like methane itself is just a carbon with 4 hydrogens. It's a gas. Not particularly interesting in the sense of what we're doing, but if you remove one of the hydrogens and connect it to something, then it becomes, then you can actually have a whole bunch of varying things with it. So if you basically remove a hydrogen from an alkane, the partial structure that remains is what we call an alkyl group. And this is the part of this lecture which is the important part. So if you remove a hydrogen from methane, the CH3 group, which could be attached to anything, it could be attached to oxygen, it could be, here we go, methyl, like methanol. If you attach it to nitrogen, you could attach it to lithium. This becomes the methyl group itself. And so if it's attached to a hydroxyl group, so it's an alcohol, you can just call it methyl alcohol or methanol. If it's attached to like an amine, this would be methylamine, which was the big thing in Breaking Bad, right? When they got the methylamine off the train. Someone's got a phone call. So you just remove a proton, the fragment which is left over becomes the alkyl group, and there's special names. So with methane, it'll be the methyl group. With ethane, the fragment which is left over would become the ethyl group. With propyl group, that's, you take propane and you remove a proton from it. So it's basically you remove the ane and you add the, so methyl. And we have little symbols for them to make our lives even easier. So CH3 just becomes Me, CH3, CH2, so the ethyl group becomes Et. And then with the propyls and stuff, this becomes a bit more complicated. But so now we know that Me basically equals a CH3, Et equals CH3, CH2. And yeah, these little lines here, this just means that they're bonded to something else. So ethanol would be, or ethyl alcohol, same as ethanol, would just be CH3CH2OH. All right, now with propyl, it becomes a little bit more interesting because remember, propyl is it's got 3 carbons, and there's different places where you can actually remove this proton from to make it a alkyl group. So you could remove a proton from the end or from the middle, and they're going to give you different isomers. So that's what we'll do next. See if I can use a little laser here. Right. Okay, so with the propane, you notice that there's 3 different carbons. It turns out that carbons A and C are basically identical, but carbon B in the middle is different than the 2 of them. Because carbon B is bonded to 2 carbons, carbons A and C are just bonded to 1. So if we remove a proton from carbon C or carbon A, you get a straight chained propyl group here, CH3, CH2, CH2. And this is just named propyl group. And sometimes they put the N in front of it because it's straight chained. So whenever you see the N, straight chained. Now, if you remove the proton from the center carbon up here, now you've got, it's bonded here. You've got a CH3 here and a CH3 here. And this is what this fragment would look like. And instead of being called the propyl group, this is called the isopropyl group. And the genesis of isopropyl is basically isomer. So isopropanol or isopropyl alcohol, OH would be here. So rubbing alcohol, you've got the OH on that center carbon. And this would be different than propanol, where the OH would be on the N carbon. So the isopropyl group is it's bonded to a carbon, which is bonded to 2 other carbons. Whereas a propyl group, it's bonded to a carbon, which is bonded to a carbon, which is bonded to a carbon. So it's just an isomer. So that's kind of, thanks. So the thing which, so yeah, so just isopropyl, it's bonded at the middle, and propyl is bonded at the end. Now, as you get more and more carbons, things are going to get more and more complicated, but it's going to stop at the butyl group. And so there's basically 4 different alkyl groups that can come out of the butyl group. One of them we're going to use all the time. So we'll look at that, and I'll tell you which one that is in a second. So remember, there's 2 different isomers of butane. There's N-butane, the straight chain one, and isobutane, the branched version. On N-butane, there's basically 2 sets of unique carbons, the carbons on the end or the carbons in the middle. And in isobutane, there is, again, 2 distinct types of carbons, the ones on the ends or the one in the middle, D. So the easiest of all of the butyl groups is just if you start from N-butane and you take a proton off the end, it's this straight chain 4 carbon N-butyl group. So you'll always see the N-butyl in front of that. So that's the simplest of all of them. If you take off a proton from either one of the 2 middle carbons, you generate 2 of these groups to be the same. So, and we call this the sec-butyl group. And where does this come from? Sec, let's just draw this out quickly. So if you've got a carbon that is only bonded to 1 carbon, like this carbon, this is bonded to some other atom here, not carbon. We would call this carbon a primary carbon because it's only bonded to one carbon. If you've got a carbon that is bonded to two carbons, we call this a secondary carbon because it's bonded to two carbons. So this carbon here would be a secondary carbon. And so that's where this, in this butyl group, it's called sec-butyl, because this carbon is bonded to two carbons. So that's where the sec-butyl comes from. And if a carbon is bonded to three carbons, this carbon is what we would call tertiary. And so we'll see in a second, there's such a thing as a tert-butyl group. So that's where the sec comes from. It's just another way of, so you can have primary alcohols, secondary alcohols, tertiary alcohols, if the alcohol functional group was on a primary carbon or on a secondary carbon or on a tertiary carbon, where you can have a primary amine, secondary amine, all these types of things. So that's where that just comes from.
There's a question in the chat.
All right, and let's see here. Where do I find this? Is there? Yes, there is a quaternary carbon. So if your carbon is bonded to four carbons, then we would call this a quaternary carbon. Now, it's you can't have any other functional groups attached to it because carbon can only have four bonds, but it is possible, yes. All right, now let's see here. So this is a sec-butyl group because it's bonded to a secondary carbon here. Now, if we take the isobutane and we remove a proton from one of the three carbons at the end, you get this crazy looking one here. And this is called the isobutyl group. And so they can't use the like a primary sort of thing for this because it's not telling us about the structure down over here. So this is a primary carbon, just like in the N-butyl group, it's attached to a primary carbon. But we need to let them know that it's an isomer of it. So this group here is called the isobutyl group. So the first carbon is primary, but on the second carbon, that's where this is technically a tertiary carbon here because it's bonded to 1, 2, 3, and it's got this these two methyl groups off of this carbon here. So that's the isobutyl group. Probably the most important butyl group is the one if you take the proton off this center carbon here. And this is what we call the tert-butyl group. So this carbon is bonded to 1, 2, 3 carbons. So it is a tertiary carbon. So we call it the tert-butyl group. And this group is really quite important. It is really a massive group with regard to atoms and the space they take up, because this carbon whereby the laser is tetrahedral. Then you move over to a carbon here, which we haven't drawn any of the protons on it, but each carbon here has got 3 protons attached to it. And they are all, of course, tetrahedral because it's sp3 hybridized. And so the tert-butyl group just takes up an enormous amount of space. So it has got, with regard to chemistry, it takes up a lot of space in a molecule, and it can actually make things unreactive just because of its size. So it's an important group for that reason. And you see it quite a lot. Like chemists use it quite a lot because it's so big. It has some ways of fixing, like, because molecules move around, right? When it's provided some energy, the bonds can wiggle and jiggle, and then they can go through different changes. In the next class, we'll talk about some conformational changes that molecules can go through. But this group's so big, it basically prevents a lot of those sort of things from happening. So chemists use it to fix it in space so it doesn't move too much, and it can tell you about the trajectories of different things when you're doing reactions. So it's been used in the literature a lot just because it's so big and bulky and sort of, yeah, it's quite an interesting little group. But anyway, so remember this one, tert beetle. We're going to see this quite a bit. Okay, and then I guess the
Here's another question.
Great. Yes, that's correct. Someone is reading ahead. Steric hindrance, right. So it's really big, and it prevents things from, because it's so bulky. Because remember, when a reaction takes place, it's the collision of atoms, and quite often, or collision of molecules, and often the collisions when they're taking place, they've got to have a specific trajectory for the reaction to work. So, and those groups can get in the way. So, okay, so the symbol R. Now, this is the wonderful symbol for those of you who, like me, who it's a great, it takes up, okay, let's pretend that I'm blabbering here for a second. Okay, so let's pretend that this is our molecule. And let's say we've got a little ketone here. And let's pretend that this ketone there's a reaction going on. It is reacting with, say, BF3. So if this ketone was reacting with BF3, what type of reaction would it be? So BF3, if we were to classify BF3, what type of
Wouldn't it be a Lewis reaction?
That's right, it would be a Lewis reaction. So BF3, is it a Lewis acid or a Lewis base?
Acid.
Right, so it's a Lewis acid. So it's got this empty p orbital, right? So if we had this, I've sort of drawn a steroid here. Steroids have got the basic structure of series of 6-membered rings connected and then a 5-membered ring on the end of it. And let's pretend that this is doing a reaction with BF3 and it makes its product. Now, the time I spent drawing this ginormous steroid, I basically, that takes quite a bit of effort, right? So what this R group basically signifies is that it could just be the rest of the molecule. It's just a generic sort of symbol that can be used to represent any alkyl group. So I could do this, for example, and do the same reaction with BF3, and I've basically saved myself a whole lot of time because I'm not drawing out all of this the rest of this large structure. So R can represent any alkyl group. Now it's true, over here I've got an aromatic ring, so that's technically there's a different functional group in there. But generally, like what the R group means is basically the rest of the molecule. And when we use it, we're assuming that there's nothing in the rest of the molecule which could react in such a fashion with whatever we're doing the reaction with. So it's just a shortcut for for any alkyl group. So it's just usually the rest of the molecule. So if you ever see R, like ROH, what we've got here is an alcohol. And it doesn't matter if it's methanol, ethanol, butanol, whatever. It's just the rest of the molecule. So that's what this little, if you ever see an R, that's what that means.
Question. For the what was it called? Ketone, but it's
Right.
textual, so it's not a ketone. But let's ignore that. The R group, could you put it on the double bonded carbon?
Oh,
I know
could we put it like that?
Yeah.
No, okay, that's a good question. Technically, no, you don't want to do that.
Because I think it's the carbon oxygen bond that matters, right?
Right, exactly. So if you've got if you've got this as, you could do it like this,
Mhm.
but it's this group here is the part which is important. So it is because this could be any alkyl group and this could be any alkyl group. This functional group would be the ketone because it's got, R represents carbon. So we got carbon on one side, carbon on the other side, so this would be a ketone. And then if we would have to do this if we wanted, say, an aldehyde. So now we've actually specified that on one side is a proton.
Mhm.
And if we wanted a ester, we could do this. And since an ester is also bonded to carbon, what you normally see is just R and then a prime to it, just to signify that it's some other carbon there, not necessarily the same as this one.
That's what I was wondering, because it's bound to a cyclic compound. So how would you indicate here for this ketone that we had that was in a ring? Should I do R prime for that one?
Yeah, you could do R prime for that one, yes. So if it was, it would just be like something like that.
Okay.
Yeah.
Thanks.
Yeah, no, that was, yeah. So that's right. So if you had, so if you did have this ROH, like this is used a bit, but so you've got some carbon here. If this is undergoing a reaction, by using R at this point, we're assuming that nothing's actually happening on that carbon and everything's happening here or here, and nothing's happening on the carbon. So there should be no reaction taking place on whatever the R group happens to be. So those components should be the inert components to what's going on. So if the proton was being removed here, you would have, then you would make R with, say, negative charge. And if this was attacking something like, say, a proton, then you would be making R, you'd be making that.
Okay, because for the carbonyl group, the carbon isn't reacting.
Yeah, but what we're going to see later on is that it's a really, because this has got a delta plus, this carbon is quite reactive.
That's what I thought. Okay, thank you.
So it's gonna like we'll get to that in a little while. Yeah. Yeah. Okay. Good. Let's see here. Right. So I basically skipped ahead for the different types of carbons. So if you've got a carbon which is bonded to one R group, so one carbon, we would call this a primary carbon. If you've got a carbon which is bonded to two alkyl groups, two R groups, secondary, tertiary, and then finally the quaternary one. Now with the quaternary one, these carbons are, no chemistry is going to take place there, because usually like if this H was a OH, this would be a tertiary alcohol, secondary alcohol. And what we're going to see later on in class is that particularly with the alkyl halides, there's a whole class of reactions which takes place in which a carbon bonded to an alkyl halide can be replaced. So it can be substituted for another group. So substitution reactions. and we're going to see that primary alkyl halides will react differently than secondary, which will react differently than tertiary. The class of reactions that they can undergo is going to be determinative by the number of alkyl groups that are there. So, but that comes a bit later on. So with the sec-butyl group, it's a secondary carbon which it's bonded to. With the tert-butyl group, it's the tertiary carbon that it's bonded to. All right. Yeah, so this is basically the classification by site. So carbon at the end, primary, secondary, tertiary. This is basically what we just mentioned in the previous slide. So that's where these all things come from. All right, now we're approaching the end of this little section, which is nice because there's, so the physical properties of, and the chemical properties of these things. So they have a low affinity for most reactions. So another historic name, they're called paraffins because they don't react with most chemicals. So they do react with in radical reactions and with oxygen during combustion reactions. So we can burn these for combustion, use it in our cars all the time. In radical reactions, it's really interesting. Molecular oxygen can easily form radicals, and it can basically remove an H radical from a alkyl chain, and then the radical will combine, so you can oxidize certain things like alkanes through radical reactions. So that's why some of the oils get rancid, is through this auto-oxidation reaction with oxygen. Yeah, we should actually, next year, I think I'm doing a class on chemistry here, there, and everywhere. And we'll talk a bit about some of the food chemistry and how things go bad and that sort of fun stuff. But that's a different class. It'll probably be pretty easy compared to this one. So think of taking that if you're bored. And so the number of carbons basically are going to influence the melting and boiling points of these compounds. So it's, as does the linearity or the branchingness. So branched alkanes tend to have lower boiling points than straight-chained alkanes because they got little, they're not like a straight-chained alkane. The molecules can pack together in a more ordered fashion through what we would call London forces or intermolecular interactions. And if it's a branched alkane and you got some little thing pointing towards, like if you got, here's my camera here. The packing isn't as nice. So branched alkanes tend to have lower boiling points than long chained alkanes. And as you add carbons to it, the boiling point and the melting point will increase. And so if you think of an oil which melts which is an oil at room temperature versus say butter or peanut butter, which are solids, what they've done is when they do the hydrogenation reaction, those double bonds make the packing more difficult, so it becomes an oil. And once you've done the hydrogenation reaction, it can pack better and it'll form a solid. So that's basically how that works. So the main intermolecular interaction for these types of compounds is the London forces, or temporary or transient dipoles. So hexanes is a liquid. It's got a boiling point, I think, around in the 80s. Whereas butane itself is a gas. It's got 4 carbons, and that would be in your lighters, right? So, and pentanes is a liquid, but anything like 4 carbons or less is going to be a gas. Like propane, we use propane in our stoves to barbecue or camp when we're camping and that type of thing. But basically, alkanes they don't react with many things, and they're going to make the backbone of our compounds, which have other functional groups which are far more reactive. And that's basically, so we're going to be using alkanes essentially as a framework for the rest of our molecules. Yeah. So alkanes are the skeleton, and the more reactive functional groups are placed on it. I think that was the last slide. Yeah. So that's basically the little introduction to alkanes. What we'll do on Tuesday, I guess we'll go over the part of it. I'll hand the test back before class. I've got some time this evening, so I'll be able to go through and give part marks and that sort of thing. And I'll hand it back. If you have any questions before next Tuesday, just send me an email. And then on Tuesday, what we'll do, I guess if you have any questions that we can answer some of those there. But what we'll start, the next section of the class is talking about conformational analysis of alkanes. So remember, a carbon is tetrahedral. So we would have, if we draw this with our lines and zigzags, so this proton's going into the board, this proton's coming towards us, this proton is in the board. The thing about carbon-carbon single bonds is that there's free rotation around these bonds. So they can spin like little mini propellers. And depending upon how the atoms are situated on the carbons next door, there can be energy barriers to this free rotation. And so what we're going to do is we're going to look at some simple molecules and what they look like in 3 dimensions and what sort of energy barriers they have with, like, when they rotate. And this will become important later on because, as I said before, there's, in certain classes of reactions, they involve collisions of molecules with each other. But for a reaction to take place, not only does the collision have to take place, it has to take place with the appropriate amount of energy, but it also has to take place, it has to collide at exactly the right location for a reaction to take place. So that's one of the things that, and when we do some conformational analysis of structures like this, it's going to give us some insights as to what that has to be like. So we're going to get practice drawing systems like this, but rather than looking at it sideways, we're going to be looking at it, if this is our eyeball, we're going to be looking right down the carbon-carbon bond and look at the locations of the hydrogens with respect to each other on the 2 carbons. So I'll probably bring a little model just to show you, and I can rotate it so you can take a look. I'll try to do that before then. But are there any questions before, because we'll end a little bit early today. Are there any questions at all? Okay, well, if you have any, just send me off an email. And as I said, I'll get those things marked and handed back before class on Tuesday. But until then, enjoy your Thanksgiving weekend. Hopefully term has gone well, given the fact that it's been a bit of the world's in a bit of chaos right now. All right. All right, see you. Yes, yes, that is true. You too. Yeah, there was a question privately about are London forces the same as van der Waal, and the answer is yes. Yeah, have a good weekend, everybody.
Hello.
Yes.
Good morning, Dr. Hell. I just have a question, please, about the lecture today. I missed almost 20 minutes from the start, and I was wondering if the lecture is recorded or not. Or
I think I did record it. I did, yes.
like, is it possible to access it in the weekend before we start the next lecture?
Yeah, what I'll do is I'll post it on Top Hat.
All right. Thanks so much. Thank you.
All right.
Thanks.
All right. Come on, little thing. Yes. So there's basically a question about branched alkanes versus straight chained alkanes. Straight chained alkanes have higher boiling points and essentially melting points. And it has to do with the way that these compounds can pack together, because the forces that are important for the intermolecular forces that are important are transient dipoles or van der Waal forces, London forces. And so when you've got a straight chained alkane, they can the molecules can pack together better than if you've got branched alkanes. Because remember, if this is your compound, one of the methyl groups would be pointing towards us, and then over here you could have one pointing towards us, and then the packing of those, things become congested because you've got groups sticking out. So it's easier to pack straight chained alkanes to than branched ones, and so the dispersion forces can work over a larger surface, and so that'll typically increases the boiling and melting points of the two structures. So if you look at if you go into like a catalog and you look up, say, octane and octanes versus just octanes, and just look up the boiling points, you should see a difference between the two of them. I don't know if that answers your question, but it really has to do with the way the transient dipoles can interact over a larger area, and they can pack better. So linear ones tend to have a higher boiling point, higher melting point. Okay, excellent. Okay. And I will